Myself Deepthi Padhyay, and I will discuss the topic normal subgroups and quotient groups in my video. As the name suggests, this topic is so easy and normal as well. You will believe me if you go through the video once, at least once. So let's start. So the normal subgroups. But before it, we already know that for some subgroups, the set of right coset coincide with that of left coset, whereas for others, this may not be true. But the subgroups for which the right and left coset coincide are important ones, and such subgroups called are known as normal subgroups. For normal subgroup, okay. Then let's see definition. Definition: a subgroup H of G is said to be a normal subgroup of G if for every X belongs to capital G and small h belongs to capital H. Have attention, small h and then capital H. Small h belongs to capital H. Then X small h X inverse belongs to capital H. Evidently, if by X capital H X inverse we mean that set of all X H X small h X inverse where small h belongs to capital H, not capital H belongs to small h, okay. Small h belongs to capital H. Then H is a normal subgroup of G if X capital H X inverse is subset or equal to capital H for every X belongs to capital G. Remark: if we have X belongs to capital G, it implies X inverse also belongs to capital G. Therefore, H is normal subgroup of G if X inverse X inverse. Let us complete the remark. Because it is incomplete, I see X inverse H X inverse to the inverse, okay. That is I read it. That is X inverse, that is X inverse Hx belongs to capital H for every X belongs to capital G and for every H belongs to capital H. Now let us see. Now we can see, normal subgroup, self conjugate subgroup, invariant subgroup, and normal divisor all have the same meaning. Now let us learn some definition. So the first one is improper normal subgroup. So improper normal subgroup is nothing but every group G possesses two normal subgroups, namely G and E. E is being identity in G. E is being identity in G. These two normal subgroups are called improper normal subgroups of G. And then second one, proper normal subgroup. First improper normal subgroup, then second proper normal subgroup. A normal subgroup H of group G is called a proper normal subgroup of G if H is not equal to capital G and H is not equal to E. Then C, simple groups. The third one is simple group. A group having only improper normal subgroup is called a simple group, or a group which has no proper normal subgroup is defined as a simple group. So a simple group G has no normal subgroup except E and G. It means, so here the point to be noted, or in simple group, the simple group is nothing but it has only improper normal subgroup, or we can say that in other words, having no proper normal subgroup except E and G. Okay, now move to next slide. Example on simple group. So the first example is every group of prime order is a simple group. So, and second example is no abelian group of composite order is a simple group. How's first example? Since a group of a prime order has no proper subgroup, therefore there's a particular case of group of prime order has no proper normal subgroup. And second, you can pause the video and read it. There's nothing point to be. Oh, this is already written. Now let us prove some theorems related to normal subgroups. Oh, pen off. Now move. So theorem 1 is a subgroup H of group G is normal if and only if x capital H x inverse is equal to capital H for every x belongs to capital G. So the proof, if x H x inverse is equal to capital H for every x belongs to G, then x inverse x capital H inverse is subset or equal to capital H. It implies capital H is normal in G. Conversely, if H is normal in G, okay? If H is normal in G, it implies what it implies? It implies x x capital H x inverse is subset of H. This is equation 1. It implies here x inverse H, x inverse to the inverse is subset of H, where x inverse is belongs to capital G. So it implies x inverse H x is subset of H. It implies x inverse H x into x inverse is subset of x H x inverse. What difference in these two equations? There is nothing. We multiply here x inverse in LHS and same in RHS, so no effect. Okay, so by combining x inverse at the same place and then x inverse, so here x inverse and x inverse I use, then it is subset of x inverse. So here it only left h as a subset of what? X inverse, so sorry, x capital H x inverse. So x inverse H is equal to EH. It is equal to E, so here EH and is equal to H. And combining this with equation 1, we obtain what we obtain? We obtain x, we obtain x H x inverse is equal to H. Okay, sorry. Now let us see second theorem. A subgroup H of a group G is normal subgroup of G if each left coset of H in G is right coset of H in G. So proof, here proof is so simple. Let H be a normal subgroup of group G, then we have to prove that XH is equal to HX for every H belongs to capital G. H is normal subgroup of G. It implies x capital H x inverse is equal to H for every x belongs to capital G. It implies x capital H x inverse is equal into x is equal to hx. So here becomes xh and in bracket x inverse x and it is equal to hx. So xh is equal to hx for every x belongs to capital G. Since x inverse is equal, sorry, x capital H x inverse x is equal to xh, it becomes E and it is equal to xh. Then what? Then conversely, let H be a subgroup of G such that xh is equal to hx and for every, this is a sign of for every x belongs to, this is sign of belongs to, x belongs to capital G, then we have to prove that H is a normal subgroup of G. For this we have to show that x h x inverse h for every x belongs to capital G. How we show it? So sorry, x xh is equal to hx for every x belongs to capital G. it implies hx into x inverse is equal to xh into x inverse. So it implies h x x inverse is equal to x h x inverse. It implies h is equal to x h x inverse. This complete the proof. Okay. Now third theorem. Every subgroup of an abelian group is normal. Here proof is if H is any subgroup of an abelian group G, then for every x belongs to capital G, we have Hx is equal to set of all small capital Hx such that h small h belongs to capital H. Then it is equal to set of all x capital H such that small h belongs to capital H. Since G is abelian, then it is equal to xh. Thus hx is equal to xh for every x belongs to capital G, and it implies h is normal in G. Here point to be noted, or we can say note, that converse of this theorem is not true. That is, if every subgroup of a group G is normal, then it is not necessary that the group G is abelian. For there does exist a family of non-abelian groups such that every subgroup of which is normal. Now theorem 4, every subgroup of a cyclic group is normal. So the proof, a cyclic group is abelian. Here we not need any long proof, because in theorem 3 we already proved that. What we prove in theorem 3? In theorem 3 we prove every subgroup of an abelian group is normal. And if cyclic group is abelian, then every subgroup of a cyclic group is normal. Proof. Now let us see an example. So the question is, let Pn be the symmetric group of n symbol. Prove that An is a normal subgroup of Pn. So solution is, so let the alpha belongs to Pn and beta any element of An. Then beta is an even permutation and alpha may be odd or even. Then alpha beta alpha inverse is an even permutation. If alpha is odd, if alpha is odd, then alpha inverse is also odd. Now alpha beta is odd and consequently alpha beta alpha inverse is even. Thus alpha belongs to Pn. Alpha belongs to Pn and beta belongs to An. Beta belongs to An and alpha beta alpha inverse belongs to An. It implies An is a normal subgroup. I hope you understand my writing. Subgroup of Pn. Then this is the answer. Now let us see and gather some information about quotient group. What is quotient group actually? So definition is, if H is normal subgroup of G, then group of the coset of H in G is called the quotient group or the factor group of H is denoted by G over H. This is not read like G by H. This is not G by H. This is G over H. Either G over H is equal to set of all HA such that A belongs to capital G. And we can also see that we read G over H in any of the following ways. We can read as G over H, also can read as G factor H, and also we can read it as quotient group of G by H. Only thing to be clear is the order of the quotient group G over H is equal to the order of quotient group G by H, this is G by H, is equal to the what? Index of H in G. This is the only concept of quotient group. Now let us move to the next slide and prove some theorem. So theorem 1. If H is normal in group G, the quotient set G over H, I repeat, this cannot be read as G by H. This is G over H. G over H is a group with respect to operation product of cosets in G. So proof, the first is closure property. Let A B belongs to capital G. HAHB belongs to G over H. Now HAHB is equal to HAB. Now AB belongs to G. Sorry, now A and B, matlab A and B both belongs to capital G. So AB also belongs to capital G and H belongs to G by H. Thus, sorry, G by H nahi, G over H. I also read G by H. This is G over H. Thus, G over H is closed with respect to coset multiplication. Now, second property, associativity. If A, B, C belongs to capital G, HA, HB, HC belongs to G over H. So, this is a sign. So, HA in bracket HB, HC is equal to what? HA, HBC. HA, HBC. Then it is equal to HA in bracket BC. It is equal to H in bracket AB and C is outside. Then it is equal to HA, HA and B, फिर HC. It is equal to HA, HB into HC. Thus, product in G over H satisfy associative law. Third property, existence of identity. Let E belongs to capital G and then for A belongs to capital G. So, HA, HE belongs to G over H. So, HA, HE is equal to HAE is equal to HA. Hence, HE is equal to H is identity element. Okay. Now, fourth property, existence of inverse. In existence of inverse, let A belongs to capital G. So, A inverse also belongs to capital G. Okay. Now HA and HA inverse both belong to G over H. HA and HA inverse both belong to G over H. And HA inverse is equal to H in bracket A inverse is equal to H. This is sign of is equal to HE is equal to H. Also HA inverse HA is equal to HA inverse is equal to HE is equal to H. Thus, inverse of HA in G is HA inverse. This proves that G over H is a group with respect to product of cosets. Thank you.